quantity. The second one is more important. Static value and then plus one, condition on x a, x naught, and not. This as a random variable is exactly the same as when. Alright. I'll keep that. So let me mention the next terminology definition. So now the super-consumer martingale, MN is a so-called super martingale, or sub martingale. If we still have the same condition, number one being adapted, and finite expected value of the absolute value. The second one is changing a little bit. Anyway, expected value and then plus one condition on the past. It's not that not. So it is a super martingale if you have the less than inequality, or sub martingale if you have the other direction. Right. Okay. To give an example, let me put there. So to give an example, maybe it's 11 here. 11. Okay. And then is a martingale. And number 1 and 5 is a complex function. And then 5 and then is a submargin. Okay. And second, if you have being a sub martingale, and 5 is convex and non-increasing. Alright, then we still have the same result. Phi is a sub-martingale. To see this, it's just basically a consequence of the conditional expectation that I have in the previous lecture 5.1. Here, let me give the proof intro. Okay. So what do I have to show? Basically, if I want to show phi Mn is a submartingale, I need to have this such inequality, right? So number 1, I need to show what expected value of phi and then plus 1 condition down x naught and naught is greater than phi Mn. Alright, that means I have 2 random variables, and I want to show one is always greater than the other. Alright. Note that I'm comparing 2 random variables. Okay, so what do I have to show? So however, this is actually pretty straightforward. Since what do we have here? I have since 5 is convex function. Is convex function. We have recalling we have expected value of 5y. Condition that next is always greater than 5 of expected value y condition that next. Alright. Recalling this property. Something I have updated in the note from section 5.1, the so-called Janssen inequality for conditional expectation. Alright. See the proof. See the proof of this in lecture note 5.1. Alright. So if you employ this inequality to this, since y is convex, we have expected value of 5 and then plus 1 conditioned on x and not, x naught and not. This is greater than 5 of expected value of and then plus 1 conditioned on this. Now we have to invoke the fact that Mn is a martingale. So this is the same thing as Mn, because Mn is a martingale. The second result is pretty much the same as previous part. But now it's a submartingale. If it is a submartingale, then this is just becomes the what? The inequality, not the exact equality. So I guess for the sake of completeness, similarly, we have basically the same thing, the same argument basically. Condition in the past is greater than 5 expected value of Mn plus 1. Condition on the past. And then because it's a submartingale and phi is non-decreasing, so this is always greater than phi of Mn. So since Mn is a submartingale and phi is non-decreasing. So that's why we have expected value of Mn plus 1 condition of the past is greater than Mn, and because phi is a decreasing function, so we have that before. As a whole, conclusion is phi Mn is a submartingale. So this thing, it sometimes could be hard to memorize the sub or the super. It could be hard. It's easy to confuse the two directions of the inequality. So I guess, okay, so maybe let me erase this. All right, let me erase. I think erase this. And maybe that definition. So I have is a martingale. All right, so we have 3P, a super martingale, a martingale or a sub martingale. If so, you have 3 directions. So a super martingale, if you are less than, martingale, that means you have equality, and submartingale, that means you have this equal. Alright. Okay, now example. Example. So suppose if I have Mn is a molecule, then Mn squared is a sub-molecule. Okay. This is clear because the function that I'm looking at is saying function phi of x is x squared. That function is convex. So since phi is a convex function, well, I guess you guys know the graph. A parabola opens up, right? So the convex function, and so phi of hence phi of Mn, which is Mn squared, is a submolecule. Okay. Yeah. But I hope for everybody knows the convexity. No? All right. Let me move on to the next equality. So the next lemma. I believe this is a lemma 5 point. I don't remember because I'm doing in the book. So anyway, it's something in the book here, so you can check this out. So we have expected value. I suppose Mn is a molecule, then certain value of Mn squared, condition of the text. So indeed, this, so we already know it is a, so Mn squared is a submolecule. We already know that. And in fact, we know this. Mn squared, alright, is indeed a non-negative random variable, which is Mn. So Mn plus 1 here. So 1 Mn squared, condition on the text. Alright. So it's just a kind of like an exercise to manipulate the conditional expectation with the adaptiveness, basically. So the proof is, I will start with the right hand side. All right, and I'm gonna, so starting from the right hand side, the square here will be void out using the quadratic formula, right? So what is this here? So we have expected value of Mn plus 1 minus Mn squared, conditioned on this. Okay, maybe let me give a name here. I don't want to write everything all over. Can I call this to be, let me call this to be x vector. Okay. So I can reduce the notation here. All right. Okay. This is, let me call it same. So this is expected value of Mn plus 1 squared minus 2 Mn plus 1 times Mn plus Mn squared, conditioned on this factor. what do I have next? So now, what do I have? So remember, if I tell you the past up to n, this is just a, basically, this is adapted to this. So mn is adapted to the past. So we have the nice property. Okay, well, I guess at least first I should split everything up. So I will split. Okay, so I have split value up mn plus 1 square condition on past, and then I have plus minus 2 mn plus 1 times mn condition on past, and then plus split value up mn squared condition on past. Right? Okay, so I split everything. So now what do we have? Because mn is adapted to the past, so this conditional adaptation is mn squared. Alright, so this is mn squared. Okay? And then similarly, because mn is adapted to this, so this can be brought outside of the conditional adaptation. So this is the same thing. Okay, so maybe let me rewrite this. Let me rewrite everything. Plus 1 squared condition on the past. So that will be minus 2 times mn times what the value of mn plus 1 condition on the past. And then the last p is just itself mn squared. Everything is because mn is adapted to the past. Right? Okay. So now we invoke the martingale property. This is just the martingale, so sorry. So this is, let me rewrite again, and then plus 1 condition on past, and then you have minus 2 mn times mn, and then you plus back mn squared. So everything coming down to mn plus 1 condition on mn, and then minus mn squared. Okay, so that is the one lemma. So now let me move on to the next one. The next lemma is the following identity. So for all 0 less than I less than k less than k and less than say I j k a. All right, we have this following expected value of n minus nk multiplied with nj. This is 0, and as a consequence, we have a probability increment, namely mn minus nk multiplied with the nj minus ni is identically given. Again, mn is a martingale, all right? Okay, so here mn is a martingale. Okay. to do this problem, actually we need a property here. So before I'm going to discuss that, I have a fact here. So the definition of martingale indeed implies the following. So as you can see, the definition of the martingale is I have the next step conditioned on the past, I have the current step. But however, actually you can condition on whatever the distance could be. And namely, implies for k less than n, and then conditioned on the past up to xk. Alright, that you recover exactly your mk. So the definition only tells you one unit. The distance is only 1 unit. But indeed, from that definition, you can have any distance here in the future. So whatever you have in the future, you condition on up to some time in the past, then you get exactly that. To see this, alright. Let me just do, let me just consider n plus 2 and n, alright. So let me just consider the following. n plus 2 conditioned on next n factorial, alright. Once you understand the proof, then you'll be able to work out for any difference. But here just, so what is this? So I claim this is indeed equal to mn, right? From that definition. So how do I get back to mn? So the idea is the following. So let me call this for the sake of rotation. Let me call this to be z. Alright. I want to show the conditional expectation of mn plus 2 on the path up to xn is exactly mn. So I want to show, so I need to show z is equal to mn squared. Right? That's what I want to show. If I want to show they are the same, that means this probability is 1. And so by the law of probability, this is equal to probability of z, b, and mn conditioned on ab, probability of ab for such for ab. So what is ab? We're calling ab is the notation for like any trajectory, so xn is the xn. Not x naught is equal to x naught, and f naught is the equal n. Right? So that's just the law of probability. So I claim here, so the goal is I will try to show this condition on such a trajectory, this probability is 1. Okay? So we note that, by definition, z and mn are both adapted to the collection of xn. So that we have, okay, so if I condition down such a path here, this is, what is that? just a constant because we in adaptiveness. So Z and then condition on A and B are constants, right? And that is just the definition of being adapted to. Okay, so in particular, if it is a constant, what is the mean? The mean is itself. This is equal to Z condition on A, B, and this is equal to expected value of condition on A. Right? If I am a constant, then I am the mean of myself. If I'm a constant, I'm not really random, right? Okay, so if I want to show these two guys are the same, I need to show these two are the same. Right?
I have a question. Why is C adapted to Xn?
Z is the conditional expected value of this conditional value. By definition, this random variable is adapted to Xn. Yeah? So I want to show these two are the same, and okay, now we have again by definition of conditional application. I have this right expected value of Z condition on A B is equal to expected value of Mn plus 2 condition on A B. If you forget this, you remember that expected value of Z 1AB is equal to the expected value of Mn plus 2 1AB. Alright? And that's why if you condition on AB, so this is just this expected value multiplied by really AB. So you remember this, then you have this. Alright. Okay. Alright. So now I have to look at this. Now, and then plus 2. 1AB, alright? This is equal to Mn plus 2, 1AB times 1 with the event Mn plus 1 is equal to let me call it to be a Y here, alright? And then a summation of 1 in the space. Okay, that just basically just split into all the possible cases on Mn plus 1. And so now what is this term? This is kind of like the event, this is actually not that. This is the event xn plus 1 is equal to y, xn is 0 x n, x naught is 0 x naught, n naught is 0 n naught. Alright? And so now because you have and what about the monoidal property, this is the same thing as Mn plus 1 AB and 1 xn plus 1 is equal to y. Alright, so this comes from monoidal property. Okay. So Mn plus 2 conditioned on the path up to n plus 1, I will call her Mn plus 1. So the value of Mn plus 2 conditioned on xn plus 1, x naught, So that's why if I multiply with, okay, so these two are like an indicator function, but basically the same as this. So like a 1 over indicator function of this event, and so I will call it this. So now you sum again. So now same thing, common. This is only the one that's running. So this is the expected value of I, and then plus 1 and b. All right. But now this is equal to, again, Martingale property. That is expected value of mn 1ab. So from mn plus 2, I go back to this, and from this to this, again, just Martingale property. And so that would imply, well, I guess up to this point. Okay, so that would imply mn plus 2, condition on A, B, is the same as mn condition on A. Okay? So, I'll be calling that is equal to Z condition on A, B. So that would imply Z condition on A, B. So basically the same thing as mn condition on A, B. In other words, probability of Z is equal to mn condition on A, B is 1. Okay. So now that is 1 coming back to this. This is equal to 1. So because I'm summing on all the A, B, so that is equal to probability of A, B, and that is equal to 1, which I need to show. Okay. Not really easy. It requires a lot of, so you have to, you have to manipulate the Martingale and the conditional expectation. Not really easy as like so I guess let me conclude here by so we have probability of Z is equal to mn in summation probability of Z being equal to mn condition on A, B or such A, B. And that is 1, so we have summation of probability of A, B, that is 1. So you can just generalize for any K and N, not only like say N and plus 2, so for any N. So now going back to that lemma that I just mentioned. All right. So now proof of the lemma. Prop 1. So what do I have to show? I want to show mn minus mk times mj is 1, so this is 0. Here I have n greater than k greater than k. Okay. So what do I have to do? So now I'm going to condition on the path up to the xk here. So this is equal to mn minus mk times mj, condition on the path up to k. Alright? And then this is the second value of the whole graph. Okay? Well, just in case you don't remember this, this is the property expected value of y is equal to the expected value of the conditional expectation of y division of x. Okay. So now, what do we have? So now mj is adapted to xk because j is less than k. So that will be brought outside here, still inside the biggest expectation. All right. So since mj adapted to the collection of my definitions, so xj, x naught, m naught, but of course this is just a subset of xk, x naught, m naught. All right. So that would imply mj is adapted to the path up to xk. So that we have expected value mn minus mk times mj condition on xk. This, alright, so this will be brought outside of here. So expected value of the big one, mj, and then mn minus mk condition on xk. Alright. Okay. And so now, what is this though?
0.
Zero, because of this. Because of this. Right. So, okay, so if you want to go further, I guess I want to say mn condition on xk minus, well, mk condition on xk. However, so this is just mk, because mk is adapted to xk, so expected value of mn minus xk minus mk, and that is 0. And so you're looking at the expected value of 0. And, well, that will imply 0. Okay. Is that nice? Yeah. It just, you see, so I just manipulate, again, just martingale property and the conditional expectation property. Right. Okay. And as a consequence, so maybe for the sake of completeness, as a consequence, as a consequence in part 2, if I have I less than k and j, sorry, I j, right, and minus mk and j minus mi is 0. So that is clear because this is equal to expected value of mn minus mk times mj, and then minus the same thing with my mk. So that is 0, basically. No. So using this orthogonality, we have following so as a corollary, we have if M is a martingale, and n minus n naught square can be split into the summation of expected value of mk minus mk minus 1 square. So this is the summation of k from 1 up to 9. So it's kind of like
Pythagorean tree.
exactly, yes, that's what I'm thinking. Right. Pythagorean, something like that. But this is actually pretty straightforward because mn minus n0 squared, that is just the same thing as mn minus 1 plus mn minus 1 minus mn minus 2 m1 minus n naught squared. Alright? And then you fold out everything. You have the cross term. Say you have the cross term between this and that, but that cross term is 0 because of this. So basically it goes something like this. So okay, so you fold out everything, right? So let me call this to be say I don't know. What do I call? I guess let me keep that. We have a summation, expected value of mk, mk minus 1 squared, k from 1 to n, and then they have the cross term, something like this. So I guess I less than j. Well, let me see if I do the math correctly. 2. So something like mj minus mj. Minus 1 times mi minus 1. Alright? So I guess this is 4. Okay? And because, I is less than j, so j minus 1, I minus 1. So they are equal. So that expected value is 0. So that is 0.